So if you did have your book, I'm doubting very many of you do. If you did and wanted to look at some things, this kind of will jump in and out of chapter 6, which is on page 395 if you ended up having it. Okay. Um, let's start with some properties to remember. So these should also be on this pink paper. Okay. So if they're on your pink paper, you want to make sure that you're looking at them on there as well. Okay, so we have different properties of equality. Okay, now in all of these, A, B, and C are any real number, so it doesn't matter what they are, they're just representing a real number. We have some basic properties which we're familiar with, the addition property, subtraction property of equality, and multiplication property of equality. These are all the properties that we use to solve equations, right? When we add 3 to both sides of an equation, we're using the addition property of equality. When we subtract 7 from both sides of the equation, we're using the subtraction property of equality. When we multiply both sides by 2, right, we're using the multiplication property of equality. Okay. Division, same thing, right? If we divide both sides of the equation by some number, we're using the division property of equality. Okay. The ones that are a little bit different for us are these 4 down here. Okay. So the reflexive property, and I should have rephrase what I said to Sydney earlier. There are certain things I do want you to write down on your paper. So find the reflexive property on your paper. The easiest way, this seems really obvious and redundant, it says that A is equal to A. Okay, this is obviously true. The best way to remember this is that something is equal to itself. Okay, and I kind of repeat that way, right? Something is equal to itself. Now, the reason we use it, yeah, you can write that on your property sheet, right? Something is equal to itself. The reason that we use this is when we're doing some sort of a proof, we might get to this point where we have one of the same thing on both sides of the equation, and so we need to use the reflexive property to help us justify what we do as we go forward, okay? And you'll see examples with it as we move, okay? The symmetric property. So the symmetric property says that A is equal to B and B is equal to A. Okay? So all we're saying is something that we've always kind of known, is that we can flip around equal signs and it's not really a problem, right? We can reverse the equation and it's still the same thing. Okay? So symmetric property is if it looks kind of like it's a mirror image, right? If the equations look like they're mirror images, then we've used the symmetric property. Okay? So I might write next to the symmetric property something about a mirror. Okay, that to me, for whatever reason, that word tipped me off a little bit. Okay, transitive property. This is the one that kids seem to struggle the most with. Okay, transitive property says that if A is equal to B and B is equal to C, then A is equal to C. Okay, now, we use this when we deal with things like the substitution method of solving systems of equations. We just don't call it that. All right. So one example of this is if we have something that says, I know that x is equal to 3, okay, and that y is equal to 3. If I know both of those things, what else do I know? That x is equal to y, right? That's what the transitive property is saying. Is if I know that 2 different things, this is what I might write down. If I know that 2 different things are equal to the same thing, then they are equal to each other. Okay. So I'll repeat that again. I say it like that a lot, and so it's probably just good to get that terminology in your brain, right? If 2 different things are equal to the same thing, then they are equal to each other. Okay. If two different things are equal to the same thing, then they are equal to each other. Okay. The last one here, the substitution property, right? People get this confused with different things, right? Just the thing about substitution that we need to remember is that if from one line of an equation to the next, we take something out of the equation and replace it, we're using the substitution property. Okay. So in this it says if A equals B, then B can replace A in any expression. Okay, so we use substitution a lot. We don't always know the best way to define it when we see it. Okay, but if we take something out of an equation and replace it with something that's equal to, then we've used the substitution property of equality. Okay, So those bottom four, reflexive, symmetric, transitive, substitution, they're the four that I think people kind of mix up with each other a lot, okay, as we go. So hopefully I've given you a couple of keywords to help remember those things. One thing that is really foreign for us is what we refer to as the distributive property. Now, when we think of the distributive property, we always think of it going this direction. So what I mean by this is we're very used to seeing a number in front of parentheses and then distributing it to the numbers inside of parentheses, right? This is what we refer to as distribution, okay? The thing that we're not very familiar with is going the opposite direction, okay? And so what I mean by this is we don't refer to, or we do something that a lot that we call the distributive property that none of you would think of as the distributive property. And what we do is we combine like terms, okay? So if we were to go the other direction, so we start with this, AB plus AC, and we get to something times B plus C, right? That's combining like terms, but it's also using the distributive property. So we never actually write combining like terms as a reason or justification for anything that we do. We always write the distributive property when we combine like terms, okay? So on your pink paper next to the distributive property, I would also put next to it combining like terms, or write instead of combining like terms, or something like that, if that's properties on there. I think it is. Okay. So instead of writing combining like terms, we will write the distributive property. So an example of what I mean about this is if we had 3x plus 4x, right? And I was telling you to combine like terms, what we've all done is we say that this is 7x, right? Because we're used to doing this without doing the steps in the middle. But what we are really doing is we are saying that what we have is x times 3 plus 4, and 3 plus 4 is 7, so we get 7 times x, right? So we're using the distributive property in reverse whenever we combine like terms, okay? So when you're asked to justify what you do when you combine like terms, you're going to say you use the distributive property, okay? All right, couple of vocab things. I'm going to have you guys help me out a little bit with this. Okay, who remembers what it means for two things to be supplementary? Adds to what? Adds to 180. So this is two angles that add to 180 degrees. Okay, you probably want to write these definitions down if you don't feel like they're in some steel trap in your brain. Okay, what about complementary? Not 360, 90. So this is two angles. This is just shorthand for angle, right? I'm just being lazy about writing. So two angles that add to 90 degrees. Okay. Let's think about the word adjacent in a non-math context. What do we mean when we say something is adjacent? It is next to. For example, who at this table over here is adjacent to Jade? Ellie is adjacent. Who else? Sydney is adjacent. Okay. Is Caroline adjacent? No. Right. So adjacent are next to. Right. So these are angles that share a side. Okay, that's the easiest way to define this. Adjacent angles are angles that share a side. Okay, so if you think about it in terms of your desks, and I'll kind of use your desks as reference points at different times. If you have a whole side of your desk that is touching someone else's whole side of their desk, right, then your desks are adjacent, right? You're sharing a side. Okay, has anybody ever heard of a linear pair before? Yes? Even if you haven't, can we break it down using what we know about these words? Okay? It is something that is linear, and there are two of them. We are talking all about we are talking about angles mostly right now. Bridger? Okay, so these are two angles that are adjacent and supplementary. Okay? So in short, they form a line, right? So an example of this is if you have an angle that looks like this, right? Here's angle A, here's angle B, right? They are adjacent and they form a line. So they're supplementary, they form a line. Okay, this is an example of what a linear pair would look like. Okay. Bisector. Who can tell me what a bisector is? Sophie, I saw you with your hands. What is a bisector? It's something that cuts something else in half, right? So we have two different types of bisectors. We have angle bisectors and segment bisectors. Most importantly is that it just is something that cuts something else in half. Okay? So we could say angle bisector, in which case it would be something that cuts the angle in half. We could say segment bisector, in which case it's something that cuts a line in half. Okay? Something like that, right? But it's something that cuts another thing in half. Okay? Now, what is the difference between congruence and equality? Somebody have an idea? Actually, let me ask this differently. When would we use congruence and when would we use equality? Equality. Yeah, equality. Anybody have an idea? When would we use congruence? Would I say x is congruent to 3? No, that doesn't make any sense, right? So why doesn't it make sense? What's wrong about that statement that doesn't make any sense? What do you mean? A constant and a variable. Okay, so when do we use congruence? When what is the same? Two angles or two line segments or two triangles or two quadrilaterals or what? So when are we using congruence? We are using congruence whenever we are talking about shapes or geometry. Okay? So congruence is always dealing with shapes or geometry. When are we using equality? We're dealing with numbers, right? And when are we dealing with numbers? Whenever we're dealing with something like algebra, right? X equals 3, not x is congruent to 3, right? Or if we're dealing with measurement, okay? So we use equality whenever we are dealing with numbers, okay? Like measurement or algebra, okay? Hopefully you remember the difference between the two signs. I'm running out of space down here, but congruence is the equal sign with a squiggly approximation on top, and equality is just obviously an equal sign. Okay? I know that's pretty low on there, right? I'll write on this board too. Right? Congruence is this, equality is this, right? So this we use with shapes, this we use with numbers. Okay? That's the biggest difference there. Okay. All right, so let's look at this. We're going to do this all together instead of having you guys do this on your own. Okay, this is in your book. If you just draw a quick sketch of that little picture over there, that'll be good enough, and then we'll be able to go through it together. Okay, so we have these two angles that are coming together. We're saying that this angle over here has x degrees of measurement, and that this angle over here has 2x minus 75 degrees of measurement. Okay. Now, generally, in a proof, we will always be given a given statement, which I'll get into that more. Basically, it's an assumption that you can make, and then you're trying to get to a certain goal, and that's usually going to be what we refer to as a proof statement. And I'll show you that in a minute when we get there. Okay, but in a situation like this, it's just telling us to justify each step to finding the value of x. Okay, so in a problem like this, we are told to assume that the ray AB bisects angle RAN. Okay? So if we're assuming that this line bisects those two angles, what can I assume about those two angles? They are the same, right? That this side is congruent to this side. Okay? Hopefully you remember angle markings too, right? One little circle means they're the same. Okay? So if I'm writing an equation, I can say that x is equal to 2x minus 75, right? Now, if I need to justify this, my justification for this would be I'm using the definition of bisector. right? And a lot of what we do will just be using the definition of something that we already know or that we take for granted a little bit, right? We knew that because this was a bisector, that would make two equal angles, right? But when we're justifying, we have to state what it is that we're doing, why we're doing it, okay? So now I want to solve for x, right? We need to solve for x, okay? So let's see. If I'm looking at this equation, Javessa, what am I going to do to solve for x from this equation? What would you do first? Okay, sure. So if we subtract x, we're going to get 0 on the left is equal to x minus 75. Which property did Javessa just use? What do you guys think? Which property did Javessa just use? We've already talked about it today. We talked about it very briefly. What's that, Cassidy? The subtraction property of equality. So my justification over here will be subtraction. And then I'm going to always abbreviate, and you can do this too. Instead of writing property of equality, I'm just going to write POE. That's going to save us some time. Okay? So, subtraction property of equality. Okay? Now what? Who has an idea? What would we do next to solve for x in this situation? Abby? We would add 75, right? And what property are we using now? The addition property of equality. Okay, now, you and I both know that normally if we're just solving a question, we'd probably stop here. But most people aren't going to write 75 equals x. What are they going to write instead? X equals 75. So if we write it like that, x equals 75, which property have we used now? Not distributive, not reflexive, symmetric, right? Do these equations look like mirror images of each other, right? They've been flipped around. So we are using the symmetric property of equality. Okay? This is the very general idea for what we are doing. We are solving things and we are justifying as we go. Okay? All right. Now, before we get to that point, before we start to get the grumblings and the moanings and stuff like that about proofs, right? Ultimately, honestly, this is the most applicable thing you'll do in math, right? And I know that some of you are probably struggling to understand why, right? But throughout your entire life, you will have to make claims and then argue why your claim makes sense, right? That's all we're doing in proofs, okay? We're making some sort of claim. It happens to be dealing with mathematics, and then we argue why that makes sense, okay? So when you will work for some boss who tells you to come up with a proposal and then to back up your proposal for why that should be done, you're just making a proof, right? You're proving your statement as to why it should work. Anytime you write an argumentative paper in English, you're doing the same thing, but your subject matter is English instead of math, right? So this is the most applicable thing that we'll do. Now, consequently, it also tends to be one of the more difficult things that we'll do. Not today's material necessarily, but the stuff that we go moving forward, okay? I want you guys to do this one with your group, okay? So you can write down the equation. The steps are all there. I want you to supply the reasons for why we could take each step, okay? As we look at this, okay, one thing to help us remember a little bit, and I think people struggle with this sometimes, is that our justification, our line on the end over here, is always our reason for how we went from this line to this line. Okay, so up here we started with our equation. That was given to you. We'll talk more about that in a moment. Okay, that was our assumption. We're assuming this is true. And then to go from this line to this line, we multiplied both sides by 2. So we used the multiplication property of addition. Okay, and then to go from here to here, we distributed the 2 to our parentheses. So we used the distributive property. And then to go from our third line to our last line, we added 10, right? So we use the addition property of equality. Okay, so you're always justifying how you got from the line above to the current line that you're on. Okay, when we do this. Okay, all right, a couple of properties of congruence to talk about. These are not new, but they are different. Okay, before we said they were the properties of equality. These are properties of congruence. They should be separately written on your paper someplace. Okay. Now, we said that congruence only deals with shapes, and that's still true here. Okay. So the reflexive property of congruence says that some angle is congruent to itself, or some line segment is congruent to itself. Okay. And when we say congruent, what we really mean is that it's the exact same length and size and has the exact same angle. Everything about it is the same, right? Exact same shape and size. Okay? So the reflexive property says that something is congruent to itself. The symmetric property says that if a line segment is congruent to another line segment, then we could flip it around and it would still be true, right? Again, that doesn't seem like it's groundbreaking information for us, okay? But that's what the symmetric property means. The transitive property is the one where people get the most out of this, okay? If I were to tell you that angle A, right, is congruent to angle B, okay, and I also were to tell you with a different picture that angle B is congruent to angle C, right, then we know that angle A and angle C are congruent to each other, okay? Even if they had different markings, right? If this had two lines in there or whatever, then we'd know that angle A would be congruent to angle C. Okay, and that's all the transitive property is saying. It's just now we're talking about it with congruence. Okay, so we're talking about shapes. So again, the transitive property, the kind of thing that I'll say with that is if two things are congruent, two different things are congruent to the same thing, then they are congruent to each other. Okay, same idea here. Okay, so let's do this one together. Let's talk this out together. Okay, so we have that picture. Go ahead and draw that picture on your page someplace. Okay, we have line segment XY. We have a couple of measurements that have been given to us. And we are being told somewhere that the total length of XY is 42. Okay, now 42 what? I have no idea, but it's 42. Okay, notice that we're dealing with numbers, so we use an equal sign and not a congruent sign. Right? XY is equal to 42, not congruent to 42. Okay, now look at your paper, and I'm going to give you about 30 seconds. I want to see if anybody can find what our reason would be for why we can make this statement. So xz plus zy is equal to xy. So comb through your pink paper. I want to see if you can find why this is true. Which property says this is true? It is the segment addition postulate. Okay? I'm not going to write out the word postulate, but segment addition. Because all we are saying is that we can see from this picture that xz plus zy is equal to xy. It's equal to the whole thing. Okay? So what are we doing here when we get to this step? How do we go from this statement up here, which has an equation in it, to this statement right here that no longer has line segments, it just has numbers? What property are we using? It's one of the first properties we talked about today that I spent some time talking about. We just plug stuff in, so what do we call that mathematically? What do we call it when we plug something in for something else? Nope, not distributive. Substitution. All we've done here is we've used the substitution property of equality, right? And this is what I meant a little bit with substitution, right? We took something out and we put something in its place, okay? So we've substituted in that place. What's the next thing? How do we go from here to here? Yeah, we distributed the 3, right? So we use the distributive property. Whoa. Don't know what that was. Distributive property of equality. Okay, then what? Okay, what was that, Cassidy? The distributive property again. What would we have normally called this? Combining like terms. But remember, combining like terms is the distributive property. That's what we are doing. That's what we're using. Okay? All right, now what? How do we go from this line to this line? Subtraction property of equality. Okay, and what about from 6n equals 30 to n equals 5? Division property of equality, right? So we're literally just stating over here what it is that we're doing. We're giving justification for the mathematical things that we're doing, right? Okay, now we'll get into this a little bit more later, but this is how proofs are normally formulated. Okay, normally they will look something like this, where we have on this side we have statements, and on this side we have reasons. Okay, so the statements over here are the mathematical things that you are saying. So in this case, we're just taking steps in an equation. Over here are the justifications for those statements. Okay, let's look at what's next here. Okay, in your groups, I want you to just talk. You don't have to write these down. I just want you to look up at the board and determine which property is being used in each case, A, B, and C. Okay, so I'm going to give you about a minute or so. I want you to figure out which property is being used in each case. Okay, so let's talk about this. Table 6. What did you guys come up with for this, for A? Okay, subtraction, do we agree with that? Okay, I'm not going to write it down if we all agree. Do we agree? Yes. Okay, table 2 up here. What did you guys come up with for B? Transitive property. This is an example of the transitive property, right? O is congruent to W, W is congruent to L, so O is congruent to L. Okay? Table 9, what did you guys come up with for C? Table 9. Symmetric property of congruence, right? Or equality. Okay? By the way, does anybody know what this means? Yeah, the measure of angle E, right? If we put an M in front of it, we're saying the measure of that angle or whatever else. Okay? All right. We're going to skip this part here. Okay? In fact, here's a little notation review. Write these down if you need to. This is angle A. Okay? And this is the measure of angle A. Right? Down here, what is the difference between these three things? Does anybody know? And this one, sorry, this one should look like this. What are the differences? What's this one? A line segment. What's this one? A line. What's this one? A ray. Okay, right? Ray only has an arrow one direction. Lines have angles or arrows two directions. Line segments don't continue on forever in either direction. Okay? It won't have arrows on the end. It'll just be like that. Okay. All right. Now, one thing before we start talking about before we start talking about proofs, is we're going to talk about baking a cake. Okay? So, these are the steps. Here are the steps that we're going to use. And you guys, when we're done, tell me what's wrong with this situation. Okay? So, step 1 is to put a pan in the oven. Step 2 is to mix the baking ingredients. Step 3 is to turn the oven on. Step 4 is to pull out baking ingredients. And step 5 is take pan out of oven and allow to cool. So, what's wrong? In a general sense, what's wrong? What? No, a very general sense, what's wrong? It's out of order, right? It has to make some logical order. How would we actually order this if we were doing this? What would be first? Number, well, I could buy 3 or 4. Doesn't really matter. Let's say for this purposes we went 1 and then 2. But this is also true. I'm actually glad this is getting brought up. There are some times when one statement doesn't depend on the previous statement to happen. So they could be said in either order. In this case, I think you could preheat your oven first or pull out your baking ingredients. Doesn't matter. Okay, but then what has to happen next? This one, right? And then what? Yeah, there's a step missing, right? We need something to go inside the pan. So we'd do that, and then we'd put the pan in the oven, right? And then we'd take it out. Okay? So the order matters. Okay? What about this one? This one might be a little more dear to your hearts here. Okay? Steps to getting your driver's license. Who has their driver's license? Jess doesn't have his yet? Okay, like 3 of you? 3 of you have your driver's license? Okay, so this has changed a lot since when I was a kid, but let's see. So, step 1 is to hop in the car and start driving with your parents. Step 2 is to go to the DMV and obtain a permit. Step 3 is to drive to school by yourself. Step 4 is to take driver's ed. Step 5 is to take driver's test to get your license. Okay. So, again, the general problem is that they're out of order, right? So the point that we're trying to get across with these examples is that just like this doesn't make any logical sense, at least it shouldn't, okay? Or definitely the cake one shouldn't make any logical sense, okay? The way that you order a proof needs to make logical sense, which means that sometimes you need to make certain statements in specific orders in order for them to be valid or to make sense. Okay? So, when we deal with that in this class, we'll try to get into what we're talking about here. Okay? Don't draw a lot of this down, but put some general idea of this T right here with statements and reasons. Okay? And then also this given and this prove. Okay, just have a little diagram. It doesn't need to have the specific words in there. It does need to say given and prove and statements and reasons. Okay, in general, this is what a proof will look like. Okay, when we are doing proofs, there are lots of forms to doing proofs. We will do them in most of the time in 2-column proofs. So that's where we have 2 columns. That's what's clearly being shown here. Okay, and we have statements on the left and reasons for those statements on the right. Okay. The given statement, okay, the given statement is your assumption. You are assuming this is true because they are telling you it is true, okay? Now, for the purpose of most proofs, that and any picture you are given are the only things that you can assume to be true, okay? But, for example, if I looked at that picture over there and I thought angle 1 and angle 2 look like they're the same size, if I'm not told that they're the same size or there are no congruence markings, then I cannot assume that they are the same size, right? We can only assume what is given and anything that has a marking on it, like this, right? Angle 1 and angle 3 are congruent because there are markings there, right? And so I can assume that, okay? Also, it was our given statement for our assumption, okay? This prove statement is your goal. This is what you were trying to get to. So this should always be the last thing you say in a proof. Okay? I've had a lot of people that don't understand this after the first day, and they put this proof statement someplace else in their proof, and then have other things to say. Right? This is your goal. Once you say that, you're done. Right? Once you can say that and you can logically get to that point, then you're done. So you shouldn't go any further than that proof statement. That's why it's down here at the bottom. Okay? You should always start a proof with your assumption, with your given statement. Okay? A lot of times proofs will build off of that assumption. Okay? I don't know, for this one, for example, the next thing you might say is something about, well, I don't know what they're trying to say. I actually don't think it makes sense what they're doing up there, but, right, we'd get through it and we'd build off of that first statement. Okay? So our given statement is our assumption. Our reason, I forgot to mention this part. Our reason for our given statement is just because it was given to us, and that's always the case. We never try to come up with some other reason for that. Whenever we write our given statement, we always will write next to it that that's because it was given to us, right? That's how come we can say it. All right. Let's see. So here's an example of a two-column proof. Okay, and this is that that one actually. Okay. Okay. So what was the reason again when we use the given statement? Given. Okay. So you don't have to write this down. You can if you'd like. Also, maybe I'll let you just take a picture if you would like to with your phone when we're done. Okay. Now, this is a lot of times what our proofs might look like, where we have a two-column proof and we have parts that are missing, but some parts that are there. Okay. Our next statement here doesn't have a statement, but it says over here that we're using the reflexive property. Okay. Now, reflexive property said that something was equal to itself. Okay. So the way that I would use this is I would say that the measure of angle 2 is equal to the measure of angle 2. Okay. Now, it seems redundant, seems obvious, okay? But we need to state it in order to make sense of what we're about to do. Okay. And then next, we're going to use the addition property of equality by adding the measure of angle 2 to both sides. Okay. We added the same thing to both sides. This is just the addition property of equality. Okay. Now, AEC, if I look at my diagram, is this angle right here. So if I look at angle AEC, what are the two smaller angles that make up angle AEC? Angle 1 and angle 2, right? They make up those angles. So I could say over here, the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle AEC. Okay. What can I say on this next line for DEB? The measure of angle what? Measure of angle 2 plus the measure of angle 3 is equal to the measure of angle DEB, right? Which property am I using here? The angle addition postulate, right? I'm using that because I've added two angles together to make a bigger angle. Okay, so I've used the angle addition postulate. Now, how do we get to the last line? That's our proof statement. That's our goal, so we're done. But we need to be able to justify what happened. So how do we go from this line to this line? Okay, let me ask this. Do we see this part anywhere else in our proof? The measure of angle 1 plus the measure of angle 2. Do we see it anywhere else in our proof? Right here, right? What about this part? Do we see this anywhere else in our proof? Right here? So what are we really doing to go from these two statements to this last statement? Nope, not distribution. That's when we're... Nope, not addition. No. Now we're just guessing. No. I had something right here, and I took it out and set it equal to what it was equal to. So I used the substitution property of equality. Okay. Now, if you want a good example of a proof, you might want to take a picture of that. Okay. Or unless you've been writing it down, then by all means, have it written down. Okay.